Okay, so this is our station 1 surface tension, and I just wanted to give you kind of a background of what surface tension is. And so when we're talking about surface tension, and we'll talk about it more in the lab as well, it's when the molecules have very strong intermolecular forces that want to keep them together. So they want to hold together, and that's when we get that mound, like you'll see in some of the substances that you'll see in the lab. Okay, and when we talk about it, it says right here, molecules with hydrogen bonds have the strongest attraction. So hydrogen bonds form because oxygen and hydrogen have big difference in electronegativity, resulting in that polar molecule. And I'll talk more about it when I do the lab. And then dipole to dipole bonds are the second strongest, if you remember from our notes. And then basic dispersion forces are normally the weakest. Okay. And so how does this really affect, maybe in the real world, affect you? Well, you have a surface tension in your lungs. So as we breathe, the air goes into those tiny pockets that are inside your lungs. And inside your lungs, it's wet, right? We've got some liquid in there. That liquid has a surface tension. And you'll see, I actually do an example in this lab that I add what's called a surfactant to something that has a very high surface tension. It breaks that surface tension, and that's actually how we breathe. If we couldn't naturally make this surfactant that breaks the surface tension of the mucus that is in our lungs, we wouldn't actually be able to go breathe and breathe out. Okay, so it's really important that we have that surfactant. Okay, and so they use that as an idea for when someone gets sick too. They can give them a little more surfactant if they're not getting enough, being able to breathe in. And you've probably also had problems where, you know, people have too much liquid on their chest and in their lungs, and that can cause a problem with breathing. So as you watch this, you'll go through the 4 different, I believe there's 4 different ones, and you'll see how the surface tension is different. So have fun. All right, welcome to the IM lab. So we've talked about a couple different intermolecular forces. We've talked about London dispersion forces, dipole, and hydrogen bonds. And we've talked about how dispersion is the weakest, dipole to dipole is the middle, and then hydrogen bonds are our strongest. So we're going to actually do a couple experiments and to play with these and see what different liquids have it. So our first one that we're going to do has to do with surface tension. So surface tension can be affected by the intermolecular forces. So we're going to use a bunch of different things. We're going to use water, we're going to use oil, ethanol, and then we're going to look and see what soapy water does as well. So let me just kind of remind you and kind of give you some information of what kind of forces there are. So I've made my little list here, okay? And so as you can see, okay, is that we have here, we have different categories. So we have dispersion, we have dipole to dipole, and hydrogen, okay? And for oil, it really has, most of it is in a dipole to dipole. Those are the IM forces that it has. Water actually has all of them. And then ethanol has dipole to dipole and hydrogen, but doesn't have this dispersion. So I want you to take a minute and I want you to think. I'm going to drop them onto, as you can see my little thing here, I'm going to drop them onto this sheet. I'm going to use a little pipette, okay, here. I'm going to take a little bit. I'm going to put them here. Look, you've probably done this at one time, putting water on a penny, right, and how it mounds up. So we're going to look at that surface tension and how different IM forces affect it. So I'm going to put water here. Ethanol is going to go here. Soapy water, we're going to see what the difference between water and soapy water. Maybe we'll figure out what happens to that water once we add soap. And then we have oil, okay? All right, so let's go ahead and get started. So the first thing I'm going to do is I'm going to do about 10 of each. So I've got my water here, okay, and I'm going to go ahead and I'm going to just drop it in here. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So you can see that the water is not spilling, right? It is making a little hill, if you can see that. So I'm going to go ahead, I'm going to see if I can get this camera in a little bit more here for you guys so you guys can see this, okay? So you can see the water is not spilling. It's kind of mounding up on itself. All right, so let's take a look and let's do ethanol, okay? And so we're going to go ahead, we're going to do ethanol. We're going to do 10 of ethanol. Let's see what happens. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So now you can see, because it's the same amount, milliliters, that I would do. So you can see how my puddle is a little bit bigger than my water. And that's because if you're here, it's kind of flatter. It's not making that surface tension. Okay, Josie, what do you think? My daughter's here. What do you think? Which one has a higher surface tension, water or ethanol so far?
The water.
You say the water?
Yeah,
okay.
Touch it.
No, don't touch it yet, Josie. No. I know. Everybody wants to touch it. They want to touch it too. All right. So now the next thing we're going to look at is soapy water. So I've mixed some soap into my water here. So I'm going to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So think about now, all I did was add a little bit of hand soap. So you can see how this is all spread out on there. Well, water is still staying together, okay? So Josie, what do you notice? What is the difference in the mound or how well that surface tension, which has less surface tension, soapy water or water? What does it look like?
The soapy water has less.
Why do you say the soapy water has less?
It's a pancake.
It's like a pancake. So she's saying, yeah, this one's like a pancake. All right, let's look at some oil. So we'll talk about in a minute maybe what happened there, okay? So let's do 10 drops of oil here. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. All right, so that is oil. And you notice oil is not really mounding up either, okay? So Josie, I'm going to have her help because it keeps running here. Which one, if you had to say, compare oil to ethanol or water, what is it more like?
Ethanol.
It's more like ethanol. So think a minute, guys, and you'll be asked this question. Which do you think has more IM forces? And Josie, don't answer. Don't give them the answer.
I don't even know what that is.
Oil or water. So you're going to have that answer. But also think about, what do you think could have happened with that when I added soap? So notice when you're looking at these IM forces, remember we had these, right? We went over these before we started. That oil only had a dipole to dipole, and it really pancaked out. So, why do you think that happened? And then ethanol didn't pancake or spread as much as ethanol, and it has dipole, and hydrogen. So why do you think that is? What caused that? And then think about the water. The water had the most little mound. It stayed there. But then we added soap. So what do you think the soap interfered with here in the water? Remember, all of this stuff is about intermolecular forces. So you can see I'm even moving it back and forth and it's spreading. So you can see how soap can affect water. So what do you think it's doing to those IM forces? Okay, and then I'll see you back for station 2. So the second station you're going to see is titled volatility. And you should understand the effects of intermolecular forces on the volatility of substance. So what does that mean? Well, have you ever noticed that some substances evaporate or turn into gas, right, more quickly than others? For instance, when you wash your hands, you need a paper towel. However, when you use hand sanitizer, the liquid just disappears. Why does that happen? They have different volatilities. And volatility is a measure of an ability of a substance to evaporate. So it's to send it into that gas. See how it goes from a liquid to a gas. Those molecules spread farther apart, okay? And it says evaporation occurs when the vapor moves away from the surface of the liquid. And then if a molecule gains enough kinetic energy to overcome the intermolecular forces, it will vaporize. So if we get enough energy, if you get enough heat going in, then it's going to cause that to break apart those intermolecular forces, okay? And so you're going to see, I'm going to test and see how volatile 3 different liquids are, okay? And how do we use that like in a medical application? Let's talk about that. So volatility is a key characteristic of many anesthetic agents. So those are the agents that we use to put people to sleep for big surgeries, okay? And due to the fact that many anesthesia medications are inhaled, these medications need to evaporate quickly so they can be breathed in. So basically, they don't start out as a gas. They are actually a liquid. And then as you can see here, she has a face mask here, and it goes through the tubes. And so they need it once it hits the air to basically go into a gas. And so it needs to have a high volatility so that you can actually breathe it in, okay? If a drug is a liquid in a vial, yet it needs to be inhaled, there are 2 ways to administer that drug when we talk about anesthesia. Some drugs are made into a spray. However, in the case of anesthesia, this would result in a lot of liquid gathering in the lungs because it must be given over time. So you're breathing this in over the entire time of your surgery, okay? And so that's why we do it as a gas. And it gets into our lungs much faster as a gas. And then it gets into our bloodstream. So it's a much faster way. If we have something that has a high volatility that'll go from liquid to gas very quickly, it's going to get into our system really quickly. So that's kind of the background of anesthesia, right? And it also says the volatility is also important so the anesthesia can leave the bloodstream. So once the procedure is over, the blood can easily release the medication into the lungs as you exhale so the patient can just breathe away the medication. The more volatile the substance, the more quickly it will leave the body. This means that anesthetics usually have weak intermolecular forces such as dispersion forces. So can you imagine? So you'll see, you'll have 3 different things. Do I want these as anesthesia? Will they leave my body? Do I want something that's going to be stuck around a lot? No, you don't. So enjoy the lab. All right, well, welcome to station number 2. So now we're going to be talking about volatility. And volatility with ion forces means how fast basically it evaporates. It goes away. And so we're going to test 3 different pieces. So we're going to test acetone, we're going to test water, and ethanol again. Okay, so remember, I mapped out for you here. So when we talked about the ion forces, that's how well those molecules stick together. So when they're volatile and they actually evaporate into gas, remember a gas spreads out more, right? So those ion forces are, if they spread out more and disappear then into a gas, then those ion forces are not as strong. So let's look at our 3 things and what kind of ion forces we might have here, okay? So we can see we have dispersion. Water is the only one that's going to have dispersion. And dipole here, all 3 of them. So ethanol, water, and acetone will have it. And then hydrogen bonds, water, and ethanol. So you can see water is going to have 3 of the ion forces. Acetone will just have 1. And ethanol has 2. So I want you to right now think about it. Okay, so water has 3, acetone has 1, ethanol has 1. So which one do you think is going to evaporate the fastest or have the highest volatility where it's going to disappear? Okay, so I want you to take a minute and make a theory, make a claim. I think, okay, acetone, water, ethanol. So answer that question as it comes up. Okay, all right, and let's get started. All right, so the 3 ones that I'm going to do, number 1 is water. So I'm going to have water here, okay? And I have some ethanol here. Okay. And then I have my acetone. And acetone is basically, you probably know it more of as fingernail polish remover, right? It's that stuff that really, really smells. So I'm going to have my daughter here help me because we're going to have to do it at the same time. So Josie, come on over, be my lab helper for me. Okay? All right, so you do. She didn't like the smell of acetone. So do you want to do the water? Because I can do two. So this is what we're going to do. We're going to take our little, not the pipettes, we're going to take our little Q-tip here, and we're going to make a line onto the black table. And we're going to see which line disappears the first. But we have to do it at the same time. Okay, are you ready, Josie?
Yeah.
Okay, so make sure it's nice and soaked.
Alright, yes.
Hold on. All right, so then we're going to put them on the table. Are you ready? 1, 2, 3, and make a line. And hopefully you guys see this. Okay. So Josie, which one's already gone?
Acetone.
Acetone's already gone. Okay.
Probably because of all the chemicals in it.
Probably, yep. So you can see water starting to kind of go. So let's see which one. It's a race between ethanol and water.
Well, obviously ethanol's going to disappear.
You think so?
Oh, look, it's mostly dried up. And
Oh, it is drying up. Yep, the water's still here. So we can watch, but acetone is already gone. It's gone. See ya. Turned into a gas, all finished. As Josie noticed, I don't know if you guys can see, but there's like some dry stuff on the edge of this ethanol here. Let's see if I can move it. So I don't know if you see this dry ethanol stuff here. So you can see that it's really starting to dry out and get smaller. Water's just kind of staying the same. So it's just kind of hanging out, being there. But this one is really shrinking, and I think I put a ton.
Ethanol are both chemical compounds, so they're
So-
going to evaporate faster.
Okay, so you have that there, and you can see now my tail. I don't know if you can see this. Let me see. My tail here is starting to evaporate, so it's getting much smaller, and you can see the dried here on the sides already. So you can see how it's kind of making a mark. This one's already made its mark there. Water's just kind of sitting there. And it may take a minute. We didn't put much on there, but it'll take a minute to start evaporating. Okay, so we'll just wait a second. Let's see. So you can see this is now disappearing. You see the ethanol now. That bottom part of the ethanol is gone. It's starting to really evaporate. So the way it went is acetone, I believe, is going to evaporate. Has evaporated already, almost immediately. And then we're going to get ethanol. Looks like it's going to be our second place. And water's going to be actually our third place person. And you can even see some of this is up here, but it's not really evaporating. So remember when we talked about the beginning that water here has all three IM forces, okay? So it has dispersion, dipole, dipole, and hydrogen. So they really like each other. They want to hang out with each other. Okay, ethanol has 2 out of 3, and then acetone only had 1. Okay, so what do you think, think about what do you think really causes the IM forces, what does that cause to volatility? Does it speed it up? Does it slow it down? Okay, all right, and I'll see you back here for station 3. Okay, so now let's look. We're now at station 3, polarity. We're not going to be comparing IM forces, but this lab is going to show you that polarity really does exist. And you're going to see it actually happen. And I want you to remember as you're looking at this that in chemistry, remember opposites attract, okay? So there are many forces within a molecule. The first thing is you should be able to identify that the more polar a molecule is, the stronger its intermolecular force. If it's got this polarity, it's got strong intermolecular forces. And the little bit of background about it, if you can remember, there are many forces within a molecule that affect the way molecules interact with other molecules. The forces are generally a result of varying electronegativity between the atoms in a molecule, okay? A highly electronegative atom attracts electrons, drawing them away from the other parts of the molecule. And of course, we always use water as a very good example of things that we can that have a very strong polarity. So with the oxygen is slightly negative and hydrogen slightly positive, okay? And so you'll see, I'll actually show you that there is a certain part of water that is attracted something. And this we're going to use static electricity, okay? But when we talk about a medical application, how would we use polarity out in the world? Why does it matter, okay? Medications actually need to bind to what we call receptors or target molecules that help it do its job, okay? It turns out that receptors have partially charged areas. So those receptors on our cells, let's say, you know, my daughter has epilepsy and she has this medicine that prevents the seizures. Well, in the cells, what's happening is she gets this over electrical kind of charge in her brain. And so this medication goes in and binds to those receptors to actually decrease that coming about, okay? And these receptors have positive and negative sides or charges. And so when we're making the drugs, we need to know what polarity the cells have, or the receptors on the cells have, so that we can model our medication to meet it, okay? So there's lots of different things. Wherever we're having this medication work, we need to look at the polarity, because remember, negative and negative repulse each other. So if it was a negative receptor, we wouldn't want our medication to have a negative polarity. We want to have a positive one so that they will bind. Okay, and so they will always think about that as they're making their drugs. Okay, so as you watch it, you'll just see that polarity. It'll prove to you that polarity does exist. So enjoy. All right, well, welcome back for Station 3. So Station 3, we're going to play with polarity. So I don't know if you remember, but we have just talked about that water has this dipole to dipole intermolecular force. So what does that look like? So I've kind of drawn out, we have our molecule of water here, right? And this is our covalent Lewis structure of water. Have our double bonds, our two lone pairs, and H. And you can see that it's, again, in the shape or what we call bent, okay? And when it's bent like this, then we definitely get that dipole to dipole. So we've got this positive side where our hydrogens are and our negative side where our oxygen is. And we call this that it has polarity. If you remember in your bond notes, he had you calculate a little bit about polarity, and that was due to the electronegativities of these two molecules, okay? So it has a positive side and it has a negative side, which means it can attract things that also have a charge. So we're going to play with actual static electricity with our balloon. And my daughter's going to help me out get the static electricity on here. And we're going to see how this affects water, all right? So I'm going to set you up. I'm going to turn this camera here so that we can see our little water. So, and I'm informed by my daughter that this is all over the internet. But let's go ahead and see what we can find out. So I'm going to move this a little closer here. So we have, and this, if you've seen it over the internet, is fine, but this explains it a little bit, okay? So we have what we call a burette here. This is a burette. It gives us a very small stream of water if we turn it on, okay? So we turn it on with this very small stream of water, okay, coming out. And so then we can start to see this begin to happen. All right, so the first step is I'm going to take my balloon. I'm going to rub it on my daughter's head.
Why can't you rub it on your own head?
I don't want to rub it on my own head. All right, so that's why I had kids, so I didn't have to do that sort of stuff. So now I've got some static electricity on here, and we're going to see what this does to our water, Okay, so I'm going to turn on my water. I have a very small stream. So let's see what it does with the water. It's going straight down into my little bucket here. But now, I don't know if you can see it, it's now attracted to my balloon. It's hitting my balloon. If you listen very carefully, shh. It's actually hitting my balloon. It's actually moving towards the balloon, the stream. You can do this at home if you have something that makes it a little, and I can just play with it, woo, and you just attract the water. So basically, static electricity gives my balloon a charge, and then it attracts either the positive or the negative side of water, okay? So you can see that water has a charge because that's how it gets attracted, okay? So now you can see how polarity can affect, right, the intermolecular forces and how that works, that different molecules can have different things. So there you go. That's how you're able to play with polarity. All right, here we are at our last station. So remember we talked about surfactants back in station 1, and we kind of saw that work when I added soap to the water and how it broke that surface tension. We're going to watch that even more here in this station here. So you should be able to investigate the effects of adding a surfactant to break the surface tension. Remember how that is really important medicine as we breathe. We need that surfactant in our lungs to break up the mucus, break that surface tension of the mucus so we can actually breathe in oxygen, okay? So in some chemical reactions, the result is something instant and unexpected. The reason for it is often known at first. In this case, is caused by the changes in intermolecular forces. So you're going to see milk, and I'm going to use whole milk, has several lactose molecules which are rich in hydrogen bonds and are also very fatty. These molecules are normally attracted to each other and create surface tension. In the beginning, the food coloring has no effect on the milk. You'll see that. And then you'll see what happens when I drop soap in it. So think about, what did soap do to water? What is it going to do there? Okay. And so when we think about medical, we can think about this with a baby's breath, okay? So surfactants are a chemical which breaks surface tension in the lungs, allowing the oxygen to pass into the bloodstream. And we all make surfactant naturally. And then think about it. When babies are born prematurely, one of the biggest concerns is that they may not have begun to produce surfactant, because we don't want them to produce surfactant when they're in the mom's womb because they're not breathing. The mom is breathing for them. They're getting the oxygen through the umbilical cord, okay? And babies don't need surfactant until they're born. So when they're born early, they may not be making surfactant. And so they can't break that surface tension of the mucus, and they can't actually breathe. And this is one of the most dangerous things for premature babies, okay? And so they have to kind of force that surfactant or give them that surfactant to help them, okay? And first, if the doctor suspects this, they'll be given steroid shots to stimulate the baby to begin creating the surfactant. So we want them to give them their own, okay? If this is not an option, so they can't give them a steroid for any reason, that's when they give them a synthetic surfactant until the baby produces it on their own, okay? So watch what happens to milk. It's pretty fun. My daughter really enjoyed it, so enjoy the lab. All right, well, welcome to our last station of our intermolecular forces lab. So now I'm going to play with a little bit of a different kind of molecule. I'm going to play with milk, but milk, really, remember, is an organic compound. So it definitely has a lot of hydrogen bonds, that strongest intermolecular force. So let's see what happens when we have milk, and we're going to add some food coloring to it to see how they react with each other. And then we're going to add some soap. Remember in that first station, we added soap to that water. And what happened to those intermolecular forces there in water when we added soap? What did soap do to those intermolecular forces? Did it increase them? Did it decrease them? just think about it for a minute while we get started. All right, so let's go take a look at our milk here. So we have our milk, okay? This is my milk. I am using whole milk because it has the highest amount of fat and hydrogen bonds in it. I'm going to add some pink, just regular old food coloring, okay? And I'm going to add 4 drops. Just very carefully, I'm going to go 1, 2, 3, 4. So notice that food coloring is not spreading or dyeing our milk because those intermolecular forces of that milk are keeping it, it's spreading a little bit, but trying to keep it from spreading. So now let's look what happens. We're just going to add a drop of detergent, just laundry detergent pretty much. Cheap laundry. Let's see what happens. Woo! What the heck did that do?
What did it do?
Come look, Josie. So you can see how it was kept in the center there, but when I added that soap, it interfered with some of those intermolecular forces of that milk, that hydrogen bonds, and it pretty much, you can see down at the bottom, I don't want to touch it with this that I have milk or soap all over, but you can see that it's not really going all the way, but it's pretty much, you can see that it's now mixing. So and you can see though from the bottom at this point, the milk, it's not all the way through, it's just on the top. So those hydrogen bonds or the intermolecular forces, the soap interfered with them. Joseph's going to stir it up for me, which is going to stir in the soap to the rest of the milk. Okay, and so that's what happens when that soap is in there. It interferes with the ion forces there of the milk, and it breaks that surface tension, just like we saw it do with water. So that's a pretty fun one. You can see how it kind of mixes and goes together. That is our ion forces lab. Hope you had a good time, and I'll see you next lab.